All right, let's take a bit more time as I was racing out of time there. A 3,000 watt panel, when sunlight is 800 watts per square meter, at 11% efficiency. That means we are only going to gather about 88 watts per square meter. This means if we want 3,000 watts and we can collect it at 88 watts per square meter, we get 34 square meters. Eyeballing these panels, they look to be about 2 meters squared each. So you'd need about 17 of these panels. This system is an actual 3 kilowatt system. And according to this company's specs behind the system, it works out to 250 square feet is what they're installing. 34 squared meters is 365 square feet. If we recalculated my example at 15% efficiency, we would get 269 square feet. So this calculation, okay, is jiving pretty well with this. They're on the more optimistic setting that this is 3 kilowatts. I'm getting it would need to be a little bit bigger, but I've chosen an efficiency which is at the low end. But nonetheless, these calculations are extremely close to what the company actually did. But it is an expensive system. Now we'll look at some energy conversion examples. These one here is a guaranteed seeing something like this. 247 kilograms is pushed off a 75 meter cliff. So there's our mass, there's our height. We're getting a potential energy change. We do this, we get that many joules of energy are going to turn into kinetic. We rearrange to solve for V, and we get this formula, and we get 38 meters a second. Now, did we actually need to use mass in here? No. It's preferable if you don't. It's less to calculate. If kinetic energy and potential are the same, then the mass would cancel. And you could have just arranged it like this and then solved. Lowers your mistake rate, lowers your time. But if you're not comfortable doing that, just plug your numbers in. Now we can visually sort of check this one out. Does 38 meters a second make sense? Well, according to this, right, 38 meters a second, we fall at each second, we gain 10 meters per second, 9.8, right? So 38 meters per second, if the first second you go from 0 to 10, then 10 to 20, that's a 4-second fall. So you would fall for 4 seconds and reach 40 meters a second. This means on a 4-second fall, your average speed is 20 meters a second. 4 seconds, it's 80 meters, which is pretty much the height of the cliff. So ballparking it in our head can actually give us that the speed should be about a 4-second fall, which is 40 meters a second. And if you can get there, that would be so nice. But I would not grade your verification on a test. It's just to prove you know you've done it correctly. Now I get a spring-loaded gun, 12-gram ball, 200 newton meters. There's our grams to, and newtons are hiding kilograms, so we can't have it like that. When we compress the spring, that's the energy we have available, and when the spring relaxes, that's the energy it will have. So the stored spring energy will turn into kinetic. And here the mass will not cancel because the spring's mass isn't part of the equation. We rearrange, right, and solve. Now what did not play here was this should have said V squared. Is that? So there's a square missing in my solution, and then we would need the square root of this, and we get 42 meters a second. Okay? Now this moron places 1 kilogram of gunpowder under a 10 kilogram anvil. Calculate the maximum height of the anvil. This is a really important kind of physics problem. We are getting our height energy out of chemical energy. So it's not potential equals kinetic, it's now the potential energy should be from the burned gunpowder. I looked up the energy density of gunpowder. It's 3 megajoules a kilogram. So the total energy that goes into burning 1 kilogram of gunpowder is 3 megajoules. All of those 3 megajoules will go into height. When I calculate the height, 3 megajoules on a 10 kilogram anvil under this gravitational field, I get 30 kilometers. What the heck? That seems crazy. Why is the answer so high? Well, first of all, when the 1 kilogram gunpowder goes off, it's not all going to the anvil. It goes in 2 directions. So at best, you'll be half of this. So you're not going to get more than 15,000 meters. Most anvils used in these competitions are only going up 100 meters are like 50 kilogram anvils, not 10. So it would be 5 times smaller than that again. So maybe down to 3,000 meters. Guns are at best 30% efficient. So if this was a cannon, then we shouldn't see more than 1,000 meters. But if you watch these things when they're launched, there is a massive fireball around this, and the anvil's already in flight. So if you watch a video of these, they're probably only like 1% of the gunpowder is going to vertical. So we get this seemingly huge departure from reality that can be worked out as one, we've got to split the energy. It goes in 2 directions. And then the efficiency kicks in and really changes our theoretical answer. And if you watch a video of an anvil toss, you can see what I mean. The vast majority of the gunpowder blasts out to the side. Now, a hockey puck isn't subjected to a whole lot of forces. So it's 170 grams and it's moving at 25 meters per second. If it strikes rough ice with a frictional coefficient of mu equals 0.4, not what I did here, for 8 meters, how much speed will it lose? Well, the thing that counts is how much friction was there. So the force of friction, okay, has to be calculated. It's the same as the force of gravity, 1.7 newtons. Then we reduce it to 40% of that value because of the roughness. Okay, so we've got 0.68 newtons of friction. The friction lasted for 8 meters. So 0.68 newtons for 8 meters gave us 5.4 joules is taken away due to friction. Now the initial puck had the energy of 1/2 mv squared, which is 53.12 joules, and friction took away 5.44 from that. So the puck has been reduced to 47-ish joules of energy. This is now our final kinetic energy, and we put it into this formula, solve for V. The puck has slowed down from 25 to 23, and it rhymed at the end. A Mini Cooper Clubman is at 45 meters a second and stops in 10 seconds. It's a rolling stop. Okay, the brakes pulsate, the wheels have to keep turning. Otherwise, if it's a skating stop with the wheels locked, the brakes aren't doing anything. The total energy in this Mini Cooper at the full speed it was first traveling is 1.4 megajoules. All of that energy has to go into the brakes. But there are 4 brakes. So this means this 1.4 megajoules is going to be divided amongst the 4 brakes. So the delta T for this formula would be Q over MC, and we take the energy, divide it by the mass of one of these rotors. Sorry, 4 masses, 4 rotors here, okay? So 4 times 9 is 36 kilograms. The heat capacity of cast iron can be looked up easily, and I get a temperature change of 84 degrees Celsius. There you go. So my little flub here is there are 4 brakes, so the mass is multiplied by 4 from this here. You have a camp stove that burns naphtha gas, Coleman fluid. It is only 40% efficient, which would be really good for a camp stove. How much would you burn to heat 1 cup of water by 70 degrees?